It's the year 1736 and Leonard Euler is faced with a problem coming from the ancient city in ancient Prussia, Konigsberg. People in that town often used to play a game of who could navigate through each piece of land with crossing the bridge once and only once. Don't attempt this problem too many times, because let me tell you, it's impossible. Now, to prove that this problem is impossible, we're going to use a field in mathematics Euler used to call geometry of position, today known as graph theory. Now, in this diagram, the points in our graph created by graph theory represent the pieces of land in Konigsberg, while the bridges are represented by the lines found on the graph. And in graph theory, these points are known as vertices, while the lines are known as edges. In the beginning, Euler pointed out that nothing mattered like the positioning of each piece of land or vertex, but the sequence of bridges crossed to cross each one once. Let's attempt this problem for ourselves. Can we cross each bridge once? I'm gonna start over here, then I go up here, down here, pass through here, here, but first try we've already missed a bridge. To prove this problem is impossible to solve, I'll go through cases that make this problem provable and end with a contradiction. In order to prove that this problem is impossible to solve, we have to take into account the degree of a vertex, which basically is the number of edges touching that vertex. More specifically, in our problem, the number of bridges touching a piece of land. The first case, or the first observation, it could be deduced that when one uses an edge or a bridge to enter a vertex or a piece of land, he or she must exit that vertex or piece of land via another edge, giving us a pair, which is an even number. Hence, it is extremely useful when trying to solve this problem to have an even degree. Even number of edges touching a vertex. Here's why these even degree vertices are useful. It's because they make entering, exiting simple. I enter, I have an exit path. I go through other edges, I enter, and I have an exit path. These even degree vertices just don't work with endpoints and start points. If it was a start point, I would use all my edges and be trapped in the center. While if it was an endpoint, I would have also used all my edges and have exited and not be able to come back in. While regarding odd degree vertices, we would have to have the number of odd degree vertices in a graph to make the problem solvable between 0 and 2. When we have 0 or no odd degree vertices in the graph, we would get a Eulerian circuit, where the start point is equal to the end point. While if we have 2 vertices with an odd degree, we would get a Eulerian path with one start point of odd degree and one end point of odd degree. If we go back to our graph, we find that every degree of every vertex is odd, which does not abide by the cases that make the problem solvable, so it's impossible. That's it, and thank you, Euler.